So let's move on to another example. Now we have a thin straight wire that carries a current of I. We want to calculate the magnetic field at a point P on an axis going halfway through the wire. And we're going to assume the leads to the ends of the wire cancel the field at point P. So essentially we're twisting the wires, so we're negating some effects. So the first thing is to draw a diagram. I know we have a thin straight wire, so why don't we draw a thin straight wire? It's going to have a length of L, and it's going to carry a current I. There's an axis going halfway through the wire. So at this point we might as well create a coordinate system where this is X and this is Y. So there's a point P on that axis Y, and that point P is probably going to be a certain height. Away from the wire. So what else do we have? When we take a look at this, I probably want to assume that this point is the origin, so we start at 0. So over here we have negative L over 2, and over here we have positive L over 2 along the x-axis. The next thing I want to do is take a look at the so I'm trying to calculate the field, the magnetic field at point P. So that means I'm going to have to break up my wire into tiny little pieces to see the contributions from each piece. So why don't we take a tiny piece here? The current's going towards the right, so might as well. So let's just do that in red so we can see this. So why don't we call this dl? And dl is essentially a small change in x in the x direction. So I want to mention that this over here is x. And at this point, we're probably going to have to draw a direct line from P to that small wire element. And we're going to call this a distance of r. And we're going to say that we have a unit vector r over here as well. So apart from this, there is an angle between r and dl. So if we kind of blow this up, we have, let's see, dl like this, and we also have our r. And there's going to be some sort of angle in between the two of them, which we'll call theta. But we also know that if we have the full length of r on the left side, then we have RH. And this would be (180 degrees) minus theta, or pi, minus theta. So let's start with the Biot-Savart law. I usually just start by writing out what dB is, so it's just mu naught over 4 pi, and I have I dl crossed with r over r squared. what are some things that we know already? First of all, I'm going to put an aside on the left so that we can continue our math on the right. I first want to figure out what dl crossed with r is. And that's simply dl times r, sine of theta. So I know r is a unit vector, so it's simply going to be 1. dl is actually dx. So I have dx times 1 times sine of theta. But there is another way of writing sine of theta, and that is going to be sine of pi minus theta. So they're both equivalent, so that means I can rewrite this as dx sine of pi minus theta. But I know that sine of pi minus theta is then going to be over here from this diagram. Sine is opposite over hypotenuse, so this is just h over r. So I can say this is dx times h over r. So I've simplified it quite a bit according to just trigonometric identities. And I know that the direction is definitely going to be in the z direction because we're going from x to y, and that means our cross product is going to be positive z by inspection. So now that we have this, we should be able to rewrite our Biot-Savart law so that we have mu naught over 4 pi I dxh over r. And r, it's r cubed. And this would be in the z direction. Is there anything else that we can get from our diagram? I do know that at some point I'm going to have to solve for dx, so this r is not very helpful down here. I should probably redefine my r. So that means I'm going to go down here and say r is equal to, I have my x and my h and then my r, so x squared plus h squared equals to r squared. So that means r is equal to the square root of x squared plus h squared. And so my dB is equal to mu naught I h dx over 4 pi x squared plus h squared to the power of 3 over 2 in the z direction. Okay, so that means I can now solve. So I have b equals to the integral of dB, and it's all in the z direction. B is equal to, I'm going to factor out all of the constants that I have, so mu naught I h and 4 pi are all constants. So I have mu naught I h over 4 pi times the integral from negative L over 2 to L over 2 of dx over x squared plus h squared to the power of 3 over 2 in the z direction. But one of the things is that we can use a known identity. We know that the integral of dx over x squared plus h squared to the power of 3 over 2 can be written as x over h squared times the square root of h squared plus x squared. So why don't we go ahead and replace that. That means I'd have mu naught IH over 4 pi. And if you do the math, you're going to end up with you have x over h squared square root of x squared plus h squared from negative L over 2 to L over 2. So we have to replace all of our x's with that, and if we do so, you end up with b being equal to mu naught I h 2L over, we have 4 pi h squared square root of h squared. Oops, not that. Square root of 4h squared plus L squared. And that's all in the z direction. But of course, I can simplify this. I have mu naught I HL divided by 2 pi h squared square root of 4h squared plus L squared in the z direction. So that would be your answer for the calculation of the magnetic field at point P away from the axis at the midpoint of a finite wire.